Hey everyone, we're going to get started. Welcome to Chicago Node.js. If anyone, after the presentation today, we'll have a few demos, just random things that random people are working on. So if anyone wants to come up and just show off something you've been working on, just let me know, or just yell after the presentation and let us know. I'll do that. If you want food and drink, there's food in the back. There's drink. You just go down this hall a little bit. There's a big drink fridge where you can grab any kind of soda you want. The passwords for the wireless are on the boards, so you can see them. If anyone's interested in presenting in the future, just let me know. You can post on the Meetup page. You can email me, smass@groupon.com, or you can come talk to me. We can talk about what you want to present. We're also still interested in doing some workshops, possibly as a separate track. So the third Tuesday of the month would still be some form of presentation, and then there would be workshops done on the side. And those would be all kinds of things, digging into various aspects of Node, and hopefully not. It wouldn't necessarily require you were at the previous one. It's one of the goals. So if you want to talk about any of those, you can come talk to me as well. And that's about it. We are starting to record and stream these. We stream them internally right now. We're recording them. I'm going to start putting them up on a YouTube account, and I'll just make an announcement to the group through email when that happens. So the previous month and all months going forward, we should have both of those things, which would be pretty cool. Yeah, that's about it.
Excuse me. Yeah, I was not able to connect. I'm not sure if others had trouble or. Yeah.
Is there one or an L at the end of them?
It's an L.
Is it?
All right. Hello, my name is Mikola. I'm actually a graduate student in Wisconsin, but my girlfriend lives in Indiana, so when I do, sort of a commute, I can always make a pit stop here. I try to time things. So today I am going to talk about a collection of kind of hobby projects that I've had a lot of fun writing. And I think they could actually be pretty useful for a variety of different things. I think this talk was labeled General Numerical Computing. I would probably not go so far as to call it like full-blown linear, algebra, general numerical method stuff. But I think that it's a start. And there is plenty of stuff left to do, but there's also a lot of things that I think this module and a collection of other packages which are associated with it give that can get us closer to that goal in JavaScript. But to maybe get started, I would first like to say why we really need to worry about this stuff, or why you should care about these things in JavaScript. So JavaScript as a language does not have a reputation for being particularly great at scientific computing. But I would actually contest that it's at least no worse than Python in theory. And Python has come to be the modern, dominant scientific computing platform of our day. And I think that JavaScript could at least give it a run for its money. And it has a couple of nice things going for it that Python doesn't, like a really fantastic module ecosystem through NPM, which puts pip and easy install and all of its other brethren to shame. And the possibility to run seamlessly in a browser so that you can package up your code and then send a demo off to someone and they can see it and they don't have to install 500 megabytes of SciPy that won't compile and run correctly on their system. So these are kind of the frustrations with Python that sort of led me down this route. And this is nowhere near the level of SciPy today, but I think maybe someday we will be. But first, let me show you a few things that you can do with this right now. So the first is like image processing stuff. So for example, you might want to be able to take an image and then apply a Gaussian blur to it at some different scale and see the result immediately. So this is all being done in real time, completely in JavaScript. It's not using any WebGL tricks. It's just regular old vanilla JavaScript being applied to an image. So another possible example is maybe you want to visualize something. So you would generate, say, like some 3D function or time-varying plot, and you'd like to be able to throw that up in a browser. So it'd be nice to have, numerical computing or, sort of array processing tools that you could throw in alongside this. And more generally, even just to interoperate and talk to WebGL, it would be great to have data structures and tools that allowed us to work at a slightly higher level than that of just vanilla binary typed arrays, so that we could, express things like different vertex stridings and orders and work at a slightly more abstract and modular sort of space. Similarly, audio processing. So here I have like a little demo.
7 years ago.
So this is Gettysburg Address, right? But we can do like pitch shifting. Yeah, it's not updating when I drag it. Yeah, so that's just that sort of stuff. I mean, it's basically, just standard like phase vocoder type tricks, right? Which are, if you try to implement them directly in JavaScript right now, pretty difficult. But with good tools for working with arrays and structured binary data, you can do these things in a sort of modular way and use them within your own applications for other purposes. So these are just some kind of, different cute examples. And I guess finally, like the last sort of like little demo on this slide here is just, generic scientific computing. So maybe you want to like solve some PDE or, simulate some system perhaps for like a visual special effect in a page, or maybe, you want to actually like take like an example model and then stick it in a web page. It would be great to have tools that made this easy and accessible in a browser. So this thing, by the way, is also, again, like all of these demos are just JavaScript, right? They're just using ND arrays. So this is like a Gray-Scott simulation here, which is a particular type of like nonlinear partial differential equation. So this is just, integrating it in time, and making the little spots replicate on the browser. So that's kind of the idea. And there's also a bunch of different people who have like built other, kind of interesting demos. I just put a bunch of links to them here. And you can, click on any of them and try them out. And there's lots more stuff out there that's, available. But this is kind of like the high level idea of why multidimensional arrays are useful and why you might care about this sort of stuff and then want to, maybe start looking into using it in your own projects. So, okay, that's the motivation. So let me try to explain now what ND arrays are and basically how you would even approach this problem of trying to build multidimensional arrays. So, okay, JavaScript as a language does not come with any built-in concept of a multidimensional array. And what it calls arrays are only like arrays in a sort of loose sense. Like they're really just objects with, a special length property and these extra, push and pop and shift and splice and so on. But they're not really guaranteed to be arranged contiguously in binary, like, CPU memory, like you would have with, say, a C array. And so you can't necessarily ensure that you'll have, consistent order for operations. So to explain how that works, right? So this is kind of like the default, strategy for implementing a multidimensional array, which is you would just declare it to be, like some indexed array of arrays. But if you think about what's actually going on in this scenario, so suppose you want to like access some element at the position 1, 2 in the array. So what you have to do is you have to first do a lookup in the first array, which will then get a pointer to the object reference for this row right here, right? So it'll basically, the first one here pulls up this row. So that takes one operation. And then the next operation has to then go do a lookup within that row to get that element. And at any given step here, these arrays don't have to all be arranged contiguously in memory. They could just be spread out wherever you want. They can be, filled with arbitrary objects. They don't all have to be the same size. Each of them has to store an extra length pointer and another pointer. So accessing an element in a multidimensional array in JavaScript right now requires like D separate indirect memory accesses. So if you want to do like a lookup in a multidimensional array, you have to do the first reference, then the next reference, and the next reference. So that's not so great. And because we have to store all of this, extra stuff for each row and column of the array, we have to store an overhead of an additional n to the d-1. So in 2D, that's maybe not so bad. You have to store a copy of all the rows here. But in 3D, you then have to store like a whole extra, image. So like if you're trying to do stuff with voxels or volumetric data, then this is not a fantastic format. And finally, if you want to just even do a walk over this array, each separate array access requires doing a new lookup into one of these tables. So it will be really, really slow and completely, scattered across memory. So it's pretty much hopeless to do efficient, array operations or loops on the regular JavaScript arrays of arrays. Now that said, though, there are a few special cases in Chrome where it can actually do some pattern matching and try to, optimize these things in very limited situations. But if you do something like, say, try to slice the array, or you pass it around, or maybe like it actually assumes that, say, this 0 here is an int, but maybe you have a 1.5 which is a float, then it tries to figure out the right type for the rest of the array, and then it doesn't pack it correctly. Like, lots of things can go wrong, and so the optimizations that you can get in Chrome are extremely fragile, and you can't really count on them. So yeah, and then finally, the slicing operation. So if you want to cut out a view of an array, you have to make a full copy of it, which requires another n to the d operation. So okay, that's the sort of simple picture for how arrays would work in JavaScript. And it's not great. And this is part of the reason why numerical computing in JavaScript is kind of bad right now. So okay, there's the other thing, which is the pragmatic workaround. Because we have typed arrays and we have other data structures that allow us to pack things into memory, you just use that. You start with a 1D array. You pick a particular ordering for the indices, and then you just arrange all of the data for your multidimensional array in memory. So for example, in this one, if I wanted to look up the element in the first row, second column, I would basically take this and multiply by the number of elements per row, and then that would be the row offset. And then I have to go add like the shift to walk over that many entries in the column. And so this is nice because you don't have to do any extra indirect memory accesses if you just want to pick some element out of the array randomly. So, I mean, you still have to do, order D multiplications, but that's like free. I mean, the array accesses are what are expensive. And if you want to do like a walk over this array in order, it's pretty fast because it's going to be packed contiguously in memory. So it'll basically scale as a function of the size of your cache line on your CPU, which is great. But the downside, though, is that you have to remember that you picked, this particular ordering. I mean, for example, I could have just as easily, mapped my indices into the array using 2 times 3 plus 1. So I could have used, instead of like a sort of row major format, I could have put it in a column major format. And you would have to keep track of that separate from the fact that, this was just a packed array. And if you want to do operations like, say, cut out a subarray or, look at some separate view, that would basically require making a full copy of the array, which is going to be very slow and pretty expensive. So this is nice if you're just working with a particular layout, and your arrays are never going to, say, leave the scope of your application or fly off, into someone else's code, and you're fine just keeping it all in some, packed format. But it's difficult to communicate this particular type of data to another object, and you don't have the ability to do things like, say, cut out a subview or look at like a part of an array instead of the whole thing. So the sort of simple modification from this implicit array style is that you basically store a stride. So instead of taking a fixed layout for the columns and in memory, you allow this to be a variable. So in the first case here, if I wanted to look at like this, first row plus this column, what I would do is I would basically multiply it with the stride, right, which is going to be, say, 3 elements per row, right? So that's basically like the elements per row. And then I have 1 element per column. And then when I sum up these indices, then that will give me the offset. So this makes it look a little bit more expensive because we now have to use these extra variables, but there's only 3 of them. And if you're already storing the shape of the array, which is, the dimensions along each axis, then storing a stride is not necessarily a big deal. So basically, memory operations just at random offsets in the array are basically the same price as before. Nothing changes. We have to store a little bit extra space when we pass around our array data, but it's not that much. It's just like, say, D bytes, so in this case, or D machine words. So we're basically storing like 2 machine words in this case. And we can do, our traversals and all of our other operations just as fast as we could before. But more importantly, what this format gives us is the ability to slice our arrays into, subarrays of arrays, or transpose them, or reflect them, or apply different transformations to them without having to make a whole copy of our data, which is very useful if we're working with some existing array or other piece of data that we got from an external source. So this strided array data structure is by no means like a new idea. I mean, this is used all over the place in C and other languages where you do have binary storage for images and data. But what ND arrays let you do is they let you apply the same concept to JavaScript. So that's the high-level idea. So And if you're, mathematically inclined, what's really going on here is that you have just an affine map from, the n-dimensional grid down to a line, right? So here's the sort of, mental intuition is that what really an ND array is it's just an affine view of a one-dimensional space, right? So that's all that's going on. And then you can just think of all of these array operations in terms of linear algebra, which is how they're actually implemented. But let me now say like how this all works, right? So how you put this idea into practice. So, okay, to say a little bit up front, I mean, there are many ways that one could imagine trying to implement this concept. The basic data structure for an ND array is very simple. It's just a strided array. And the core ND array module doesn't do a whole lot. In fact, it's like almost nothing is in there. It's basically just the simplest tools that you need for working with views of arrays. And the way that you expand functionality in ND arrays is you don't just add something into this gigantic framework or, you want some, like little pet utility function right away. Instead, what you would do is you just create a module, you put that module on NPM, and then you can add this functionality to ND arrays by just requiring whatever modules you need. You don't have to like patch, some framework. You don't create a plugin. You just create functions. They use ND arrays, and that's how they talk to each other. That's it. And all of this stuff works, of course, in the browser using Browserify and on Node.js. And there are good reasons that you would want to do both, because maybe you want to do some image processing or array operation on a server, and then maybe push that down to a client eventually. There's lots of places where just these tools are fairly generically useful. The other thing, too, is ND arrays do not manage memory for you. So basically, the ND array is just a view. It doesn't have any call to like new float 32 array or allocate anything for you. That's up to you to handle all memory management. So if you want to like make your own ND arrays or handle your own memory allocation, that's your responsibility. It's not the ND array modules. And the last thing is that because they are all built on top of typed arrays, it's very easy to get these things to talk to WebGL and then build things like complex vertex formats for meshes, which you can do by slicing. And, I'll say a little bit more about that. So, okay. So first order of business is let's look at the interface for ND arrays. So the basic idea is if you want to use ND arrays, is you would require them, just as any other module. And then to create them, you just call the module.exports or your default function, and then you pass it in a set of parameters. So I'll explain what these are now. The data parameter is just the underlying 1D array. So that could be either a typed array, a buffer, even a regular vanilla JavaScript array. And you can actually even implement your own custom data storage that you can pass into there too. Then you give it a stride parameter, or no, a shape, which is the size of this array in memory. So these are basically like for each of the different axes. So you could pass in like say mn for the 2D part of the array. Then you give it the stride, which is the arrangement of the array in memory, and then an offset, which is just the shift value that gets added onto it. And you can skip these things too. So for example, if you just pass the data, then it'll just create a 1D ND array, which can be useful for various things. Or if you just pass the data in shape, it'll basically assume that you're using a row major format, just like C++ or C, and it will build a stride and offset, which is automatic. So you can, there are basically like little sort of shortcuts for common cases that you can use here. But this is the full, constructor. This is what you get. And what it will return is this object array, which is a view of the underlying array data structure. And once you have this view, you can then access elements in it. So this is sort of like a debugging. So you can do stuff like, array.set, and you pass it a pair of indices and a value. And then it will basically translate into, take the data property of your ND array, multiply it with the stride, add your offset, and then update the value, right? So there's also accessors for get, set, and index. And you can use these things to, just update them. Now, in general, you shouldn't try to write like loops or other operations, and I'll come to this in a moment using the syntax. But this is basically just like, to quickly get at the different elements of the array. So this is just the, simple debugging or easy setup type of convenience function that you get. So, all right. Now that's the sort of basic stuff. The more exciting sort of features that you can do with ND arrays are you can do slicing operations. So you can truncate the array. So you can basically shrink the size by, basically calling the .high method, which will create a new view that has a smaller size than before. or you can move the lower left corner of the array, effectively shifting the offset by basically calling .low. You can also transpose the array in constant time again. So you basically are just permuting the order of the indices of the strides. You can change the rate at which you step through the array. So you can do stuff like, say, take every other pixel, which would have the effect of downsampling an array, for example. And you can also select subarrays, which allows you to, say, pick out like a particular row or a particular column, and that'll give you an ND array that just represents that one row or column. And you can chain these things together. So each view has basically ordered dimension space, so each of these operations is effectively like ordered D technically, because you have to allocate that many bytes, but it's not a big deal. So, okay, to kind of demo this, I put together like a little live coding type thing here. So here's basically how this works. So you can type in some slice expression here on array, and then what you see in the corner here are the different properties of the array. So this is basically the expression that I defined here, which is defining some slice of this data array. This is the shape of my slice. This is the stride for this thing as it's arranged in memory. And this is the offset. So what I have here is I have an image, which is encoded as a 3D ND array. So the first two components are the basically rows and columns of the image. Or actually, I think this is flipped. So it's, yeah, rows and columns. Then the next component is the color. So you have basically a 512 by 512 by 3 array. So to get started, let me first show how high works. So if I take, say, 256, 256, this will cut the top left corner out of the image. All right. So if I type .high, it'll move the lower right corner to some new position. So I can type in another value like 128, and it'll move it there, or 512, and it'll move it all the way to the side. I can do other different things like. Okay. So that's the .high method, which basically moves the corner around in the image. The next method that I want to talk about is the .low, which moves the upper left corner of the array around. So I can do something like, say, .low 100, 100, and that'll move the corner there. I can move this to 256, and it'll be at a different location. So basically, what I'm doing here with this .low is moving the upper left corner of the array to different positions. Right? Okay, so that's the easy stuff, right? Which is basically just cutting contiguous subregions out of the array. Right? Now here's something a little trickier. So I can do transpose of the array. So I can do something like this, which will basically flip it to its side. Right? So what this is doing is it's just changing the rows and columns of this image around and creating a new image in place. So that basically will just reflect it, or it'll rotate it about some axis or exchange two parameters. The basic syntax for transpose is you just give it a permutation, and then that permutation will be applied to the indices to create a new view from the array. Okay, now the other thing I can do is I can change my step. So this basically changes the rate of the stride. So if you look here, like my previous stride, so previously the stride was 3, 150 or 1536, and then 1. If I do .step 2, 1, it basically makes this thing step, twice as fast. So now its step is 6, and the image is now squashed. Right. So basically, what I'm looking at in my data here is I'm taking every other scan line. Right. And if I change, the second component, then it'll now take like every half pixel. So I've effectively downsampled my image, to like a little thumbnail size. And I can increase this too. I can make it 3.3. I'll get an even tinier image, and then it'll be taking even smaller pixels. I can do something like this. Now you can also do things like pass in a negative value, which will reflect it, and it'll just step negatively. I mean, all it's doing here, right, is if you look at it, it's just changing the stride to the negative value and modifying the offset. So all of these operations, any linear transformation of your data can be encoded by just modifying these parameters. It's just, multiplying matrices together. And then you can combine these things too. So I can do something like this thing, transpose 102. Now it's reflected and flipped, right? In just one line. So that's all that you have to do. And similarly, if I want to take out like a subview of this thing, I do something like .low, 128, 128, .high, 256, 256. And then this will just cut out the region in the center of this. So what I did was I basically moved the lower left corner to here, and then the lower the upper left corner in, and then the lower right corner up, and then cut out this thing. One thing that is worth pointing out, though, is that high and low don't necessarily commute. So this sort of syntax where you do low, high would be how you would specify cutting out an interval. But the opposite version will basically cut out an interval first and then cut a subinterval from that interval. So if I do something like dot high 256, 256, dot low 128, 128, then it'll basically first cut out this region and then loops the corner in. So it's not the same, right? Hopefully that makes sense. I don't know. I mean, you can also apply these things to the color channels. So I can do stuff like take only the red component from the array, and I'll just get that from there. Or I could take just say the red and green components, and I'll get the yellow part of the image. Or I could take basically the blue part, and then this will basically give me just the blue component of the image. Or I could even do something like switch the colors around too. So I can do something like step 1, negative 1. So this will basically flip the red and blue color channels. So yeah, this is just basic playing around with slices. Am I for time? Okay, I think that's enough to say about this right now. If there are any questions, I guess I could try to answer them. Or I'm just going to go on with the rest of the presentation. You can also get these slides online and then try playing around with this demo yourself, and maybe it'll be a little clearer.
Question, actually. So you did all of this using your NDARRAY implementation, right?
Yeah.
What if you did it like using regular JavaScript?
It'll be very slow is basically what will happen, right? Because basically each of these operations is constant time. If you do it with a regular array, you have to make a copy every single time you do that.
So we would actually see the performance difference, right?
Yeah. I mean, that's basically what it is. Now, this is just a demo illustrating how slicing works, right? So for something this simple, you could probably even do it with like regular arrays of arrays. It's not going to be that big a deal. But what this is illustrating is what you can do with the slicing operations, right? And then from this, you can build up more complicated things. So where slicing can become very useful is if you have, say, for example, in voxel.js, this came up, where you get like data from, say, different voxel formats, like, for example, a Minecraft region, and then maybe, like the order of, say, the X, Y, Z coordinates in the Minecraft voxel data is different than the internal representation voxel.js uses. So with NDArrays, it's just a matter of calling transpose, and then it all works, and you just pack the data into the array. Whereas if you did it using, like, say, a fixed size array, then you would have to go through and manually change a whole bunch of, assumptions in your code or do lots of extra memory copies in order to move things around. Whereas this just operates in place in constant time. So it's faster, right? And it's simpler.
So each of those operations, is it not copying the underlying data?
It's not.
Different views on the same data? It's
just changing the view. You can see what the view looks like here. So in this case, this is like what the current view is. So the shape of the view is 512 by 512 by 3. The stride for this view is 3, 1536, -1. And then the offset is 2. So basically, this is like the number of bytes per each row. This is the number of bytes, or the number of, like the step per row, step per column, and then step per color channel. And because I flipped it over here, the color channel is stepping at, -1 per byte. All right, so that's, or -1 per index. So, okay, that's the basic idea of slicing. That's probably the hardest concept in this whole lecture to get around. And the last thing I want to say about NDArrays in the core module is that you can also pass them a custom data type. So at the moment, like what I showed you there, that was using typed arrays. But you can also do something like create a custom like hashed or sparsed data structure, and you can pass that to the NDArray constructor. And then it will basically do indexing into that 1D array constructor. And then all the same slicing operations still work. So it won't make a copy of your underlying hash data store. It'll still just be a view of that. So all that you have to do if you want to implement your own custom NDArray data structure is you just create a one-dimensional data storage format. And then all of your operations are just views of that one-dimensional data storage. And so this can be useful for implementing things like bit arrays. So if you want to only store like just bits for like a giant bit vector, then all of the same tools still work. Or if you wanted to do something like make a hash-based thing for like a very sparse array, if you want to run length encode it to create CSR or CSC type matrices, the same idea works. So that's it. So now with the last the next 15 minutes, I want to just go through a bunch of different modules. So that's the core NDARRAY module. By itself, I have to say, it doesn't do much, right? So it just is a language for working with views. And so the reason that we have to have this language is because we need some common way to pass around multidimensional arrays, right? So the goal with that module is to keep it as small as possible. And I promise, as best as I can, that I will not allow any features or changes or any API modifications to the original core NDARRAY module. I'm hoping that it is mostly finished or mostly fixed. I mean, assuming that there's no bugs or any like horrible misconceptions or like bad ideas that show up, right? If they're bad enough, I'm just going to fork it and make a new thing. But the core NDARRAY module, I believe, is done. Like, you don't have to change that anymore. So hopefully, fingers crossed. And so the way that you would extend functionality is, and anyone can do this, is you just go out, create a new module on NPM that can consume or produce NDArrays, and then you can use that to talk to other modules. So one of the most basic ones that's worth getting to know is NDARRAY-OPS. And so here's kind of the syntax for it. So you basically load it just like any other module, install it from NPM. And then you can basically do component-wise operations. So for example, suppose you want to multiply an array by 2 for each element inside there in place. So the sort of general idea for each of these things is you first give it the operation name. So in this case, it's .mul. Then you can basically say if you want to have a scalar parameter or an array parameter. So in this case, I'm basically passing it a scalar. And then this is basically the in-place update flag. So if you pass this .eq on here, then it'll update a in place. Otherwise, you'd have to give it 2 arguments that you're going to update the array with. So there's a lot of other different operations. In addition to all of your basic arithmetic stuff, like you can take the difference of 2 NDArrays, subtract them. You can multiply them together. You can compute, absolute values, raise them to a power. There's also operations for assigning. So if you want to just copy a subarray into another one, which is a very common thing to do, you can do ops.assign. And you can also initialize an array with a scalar using ops.assignS, following the same convention. So this is just like a bunch of pre-baked little utility functions that are ready to go. And the reason that you want to do this, and the way that they're all implemented, is with this other module that I made called CWise, which is kind of the scary internal details for how these things are built. And if you want to do more complicated component-wise operations, it's worth trying to understand how this module works and using it. The basic idea, though, is that what CWise does is generate cache-efficient loop operations on these arrays. So for example, if you have an array that's like in row major order, the best way to iterate over that array is to just walk over it lexicographically in memory. That way, each time you're doing a new array operation, you're going to be pulling in 1 full cache line worth of data, and you can operate on that and push it back out. So you'll get the maximum efficiency out of your memory bandwidth. But if you walk over an array that's in that order, if you walk over an array in that order, but the array happened to be in column major order, so it's flipped in memory, then you're actually doing the absolute worst thing. Because what will happen is every time you access a new array element, that previous cache line that you pulled in didn't have anything to do with your next values that you're going to pull into memory. So that's not good. And that will make your array operations go really, really slow. And this is also why, in general, you don't want to write array operations using get, set, or those other operations yourself. Unless you know precisely what you're doing and you know the format for your data, right? So if that's all controlled, it can still make sense to do that. But in general, the better way to do it is to use this module, which will generate the loops. And it also handles the trickier case where, for example, you have 2 arrays coming in as an argument. One array is in, say, row major order. The other array is in column major order. And you would like to be able to do the correct cache-efficient thing for that pair of transposed arrays. And so the way that this is done in NDArrays is it uses what's called a cache-oblivious algorithm, where it basically recursively divides these arrays in half, and then basically splits them into tiny blocks, and then it executes the operation on each block. And that means that basically what you'll do is you can read in a full block's worth of cache lines for both of the arrays in one shot, and then those will all be hot in memory, and then you don't have to worry about this, fetching or pulling stuff out there. So that's complicated, and it doesn't work for just 2D arrays. It actually works in full general, arbitrary dimensions. So it actually, this is the sort of simple picture, but this idea, generalizes, I assure you, completely straightforwardly to, whatever dimensional array you want to work with. So if you have a 3D volume, it still does the right thing. So that's the guts of this. I'm not going to spend too much more time talking about it. So okay, those are the low-level things. But now once you have that, then you might want to say get them to talk to WebGL. for example, and I have a collection of modules that I've written for that. In particular, there's GLSLify, which is sort of a very neat project by Chris Dickinson, which adds NPM style requires to GLSL as a preprocessor macro. So that's definitely worth checking out. And there's also these other tools, GL Texture 2D and GL Buffer, which allow you to upload ND arrays and transparently manipulate vertex data on the GPU. So these are just kind of like things, they're very low level, lightweight wrappers that just encapsulate specific components of the WebGL API. They're not something that attempts to be like a massive framework with a scene graph and a bunch of other complexity, like say 3JS or all these other different things. It doesn't even tell you how you have to arrange your meshes. You can use whatever vertex format you want, and with ND arrays, you can even encode it and specify it. So, okay, and then there's a lot of different utilities. Pretty handy one is ND array pack and unpack. These let you convert between the original native JavaScript arrays for testing purposes back into regular ND arrays. There's ND array fill, which you can use to initialize an ND array with some data. It's pretty handy for a lot of applications. It's kind of, you can think of this as like CWise light, right? Like basically it's not quite as fast as CWise, but it does okay. There's also pool, which is basically really useful for memory management. So oftentimes you might want to create some scratch memory. Basically typed array pool lets you do manual memory management with typed arrays in JavaScript, which is very useful. Then there's image processing stuff like save and get pixels, so you can load an ND array into an image or save it back to disk. And then there's some debugging stuff. So another nice one here is ND array imshow. I don't have this loaded up right here, but basically this lets you like log ND arrays into Chrome DevTools console or pop up a window in Node.js. So you can be like debugging the array and pop it up. I may show that afterward. And then there's string operations, so you can turn strings into ND arrays. And then there's more stuff, so you can do FFT, you can do sorting, binary searching, Euclidean distance transform, so this is like find closest point. To some extent, matrix multiplication, this is still a work in progress here. You can voxelize a mesh into an ND array, or trace like an image, like rasterize a polygon. There's bitmap ND arrays, hash table back stuff, sparse run length encoded things, and a whole lot more. So this is just like a kind of high level overview of the modules. There's more stuff too. There's also stuff to do surface nets like triangulation, extraction, or curve tracing. I may show some of this stuff. Okay, but so here we go. This is a lot of ideas. So let's go through kind of a quick example, I think, with maybe the last 10 minutes here, to just show how to do something interesting with ND arrays, like a sort of example computation. So what I picked for this is I'm going to do a naive implementation of the Burrows-WHEELER transform. Which is, if you haven't heard of it before, it's basically like a tool that's used in data compression to kind of generalize like Huffman encoding. So normally like Huffman encoding will only compress like one character at a time, but if you do the combination of Burrows-WHEELER transform plus run length encoding, then it's equivalent to encoding like up to k characters at a time for the optimal choice of k. So it's kind of like a better way to do entropy encoding for strings, right? It's used in bzip2. So if you know bzip2, this is the algorithm in it. Okay, so here's the idea. So first, the sort of simple starting point for this is that you have to give it a string. So for now I have picked banana, but we could do something else. We could do something like banana with like multiple A's. Doesn't matter. Okay, and then so what you do in the Burrows-WHEELER transform is first you generate a matrix of all shifted copies of the string with itself. So what I'm doing here is I'm using the ND string module, which will basically take my string here, and it creates, and I basically take the string concatenated with itself, then I'm going to build a 2D ND array with a stride of 1, 1, and an offset of 0. So what this is going to do is I have an actual, like a single array, which is basically banana, banana concatenated with itself, plus the 0 terminal character there. And then I'm basically building a 2D view of that 1D array. So the actual data itself is of length 2 times n, right? And then the array is going to look like shape n squared or n by n, right? And it just has this stride that's 1, 1. So it's like a slightly degenerate kind of array. It's not fully packed in memory. Okay. And by the way, like all this stuff updates too, so I can do stuff like add more A's there, and I'll just generate more columns of the shifted thing. Okay. So the next step in the Burrows-WHEELER transform is that you then sort the rows of this matrix, right? So basically, what I'm going to do here is I'm going to go create a quick copy of this array using ND scratch here, which will basically like allocate it in scratch memory. And then I'm basically going to sort the rows. So what I did was I took this initial matrix here. I just sorted by the lexicographic ordering on these strings. And then the final Burrows-Wheeler transform is I take the last column. So what I'm going to do is I'm going to call .pick, which I didn't show that in the slicing demo. I should have said something about that. But basically, pick takes out a subarray. So what I'm going to do is I'm going to pick the last column of this matrix, right? And that's this guy here. All right. So that's the Burrows-Wheeler transform in like one page of code. So if you actually look at it, excluding the requires here, there's just 1, 2, 3, 4, 5 lines. That's it, right? So it's pretty concise and compact, very simple way to work with like arrays and very easy kind of simple example. There are faster ways to do the Burrows-Wheeler transform, by the way. This is just the simple demo kind of conceptual picture. All right. So, okay, now let's do the reverse. So we can now show that this reverse banana here can actually be undone. So first what we're going to do is we're going to create a matrix of all of the shifted copies of this string, which will look like this, all right? And then what we do is we just keep recursively sorting the last 2 columns. So basically working from the right back, we're going to keep resorting the sub-arrays. So that's basically what I'm doing with this .low here. So each time I click, I'm going to sort another column. So basically I'm going to sort now this section of arrays, click again, sort again, click, click, and now we're done. So we've now recovered our original string. So that's kind of the idea. We can come up with like a more complicated example. So I'll just go type in another string, like, all right, just some random thing. We have their same. This is our Burrows-Wheeler transform string right here. And then now we can go do the same thing. So we'll just step through it. So sorting the columns from the right. There we go. So, all right. And then we just take the top row of the table, and we're done. So that's the inverse Burrows-Wheeler transform. Again, it's just, say 1, 2, 3, 5, 6 odd lines, right? So pretty short, very compact, and it's easy to do this when you have all the right modules already, out there to just grab and throw together. So that's, I guess, NDARRAYs in a nutshell, and I think I'm out of time. So what I want to say, though, is that there's still a lot of stuff left to do. So most of this stuff has basically been like raster operations and basic array manipulation. But long term, I think linear algebra is the big thing to do. And I think the right way to approach this is eventually to try to get some way to take existing C++ and Fortran code and maybe somehow through Scripting or whatever, find a way to put those into modules and put them on NPM. Or maybe we'll just have to re-implement everything in JavaScript. I don't know which is going to happen, but that would work. Sparse arrays are already kind of there, but it would be nice to get better integration with them. I think that it can be made a lot faster. It's just not there yet. Tensor operations, so right now I can do component-wise, but it would also be great to do like 3D, 4D tensor contraction things. That would, and the same cache oblivious type of approach ought to work. There's also more to that too, but I'm not going to say anything about it. And finally, more debugging tools. There's already some stuff with this, but more is always better. I think one thing that would be great would be to put in like, some sort of optional version of NDARRAY that can do bounds checking, perhaps, would be kind of neat. I need to think about the best way to kind of integrate this into the system. And then finally, also like raising more awareness, because I mean, like NDARRAYs has a lot of stars on GitHub or whatever. It's not huge or by any means, but the problem is that everyone stars like the wrong thing. They all like focus on NDARRAY, which there's nothing in there. It's the modules you build with NDARRAY that are important. And the lack of stars, for example, on things like ops or CY suggests to me that a lot of people aren't using this, or if they are using it, they're not using it properly. So I don't know. I think that there's not a lot of understanding right now out there about what all this is about. And so there's just lots more stuff to do, but it's a good start, I think. And there's some more info. Here's some blog posts I made, and then there's also modules.gl, which uses NDARRAYs, and some acknowledgments. So these are various people who have helped out or contributed with this project, and that's about it. So I think it's now 7. I'm going to wrap up this presentation, and I guess we could do demos or something afterwards, if anyone has patience for that. Otherwise, I'll just take questions, and I guess you're free to go if you want. So, or maybe I don't want to release them yet. I don't know. Whatever. Okay, any questions?
What if you have operations that require higher precision math? You need to get into like arbitrary precision. How do you typically how do people typically handle that with the ND arrays? Do they use like big number or some other library?
So usually array processing and high precision arithmetic are two kind of orthogonal things. I don't know of anyone doing like, say, like raster operations or big linear algebra that gives any damn about big precision, right? I mean, basically you just don't have the capability to do that with a giant array. So the way I look at it is like higher order precision is just an orthogonal problem and not particularly important in terms of what you want to do with ND arrays. But it is interesting, I think, and it is something that is worth trying to do. But I think it's probably more important in like the crypto and like combinatorial geometry world rather than in like the numerical scientific computing space. So yeah, I think it's useful. I just don't know if it really fits in with this at the moment. Any questions at all?
So for the slicing operation, you basically construct a new array with the desired traversing word order, right?
Mm-hmm.
So that you need to push something into that array, so that seems very fast.
But it does not modify the array. All it does is it just creates a new ND array view. That's it.
So the view itself is another array, right?
It's a view. It's not. It doesn't actually have a copy of the data. It just has a reference to it. So each ND array is a view of a 1D store. So it's a multi-dimensional view of a 1D array. That's all that they are. So they're basically like some linear affine map down to a 1D array. That's all. So you can think of it as you just dot product with the stride at the offset. That gives you the coordinate.
So is there a way to, you have to pardon my ignorance on this, is there a way to do really super complex math operations with the GL stuff that would map to some of the functions that you have there?
At the moment, not so easily. I mean, if you want to do complicated GL stuff, it's better just to write it in GLSL, I would say, rather than try to like port JavaScript to make it work on there. I mean, the other thing too is right now, none of these operations are set up in such a way to run on the GPU. They're all in JavaScript, and that's actually kind of useful for a lot of things. But yeah, it would be nice to use more GPU stuff, but there are problems. So one issue right now is that in WebGL, there is no way to read data back from the GPU efficiently. Pardon me. But basically, like if you write an array of floats out in a float texture, which you can hypothetically do, there is no function that lets you read floats back from the GPU. You can the only thing you have is you have GL read pixels, which is a synchronous operation, and it's very slow, right? And it can only read back up to 4 unsigned 8-bit bytes from the thing at a time. So basically, you get like a packed, 32-bit image format that comes back, and if you want to read out floats, you then have to encode those floats into the bytes, and it becomes very slow. And at the end of the day, even if you did the computation on GPU and it was crazy fast, the process of uploading it to the GPU, reading the pixels back, and then unpacking the floats that you just worked into it is just not justifiable. It doesn't make any sense to do it, I think, on the GPU today. So if you want to do GPU code, and I think it does make sense to do this for many things, you want to keep it on the GPU. And the way to do that is you first push everything to the GPU in some initialization step, and then you just update everything with shaders. You don't even touch it on the JavaScript side, because there's just no good way to get that data out of there fast enough that it would make any sense to do it. But maybe this will change with WebGL 2. I don't know. They have a lot of crazy ideas for that, so I have no idea. I mean, perhaps it could be different, like 5 years later. I don't know. Sure.
We have a blog post or website that describes ND arrays.
Yeah, the kind of basic idea behind how CUIs works. Oh, I'm not on the internet here, but if you click on that link, it'll get you there. So these little blog posts will work. So I will say at the time I wrote this, I did not think that these were going to be terribly important, but at the moment they're kind of like the only real sort of technical explanation for this stuff. But eventually this will change. This will get better, I hope. Yeah.
I'm not very familiar with the ND array module, but are there any real-world examples people are using it, and what are they using it for?
Well, it's being used all over in voxel.js right now, and I've used it for a couple of internal projects at 3D Systems, and modules.gl is built on top of it. But it's kind of new in a way. I don't think that there are too many people out there, besides myself and like maybe a couple of friends who are like actually doing anything with it. So part of the reason for giving this talk is to raise awareness of this so that other people will go out there and try building stuff with it. I would say at the moment, probably stick to hobby projects more than anything, right? It's still like a very, in a way it's been around for almost a year now, but still, it's like a hobby thing. The core NDARRAY module should be fine, but, other stuff is always evolving.
So let's say if we have a project that uses a lot of arrays, 2D arrays or 3D arrays, so this would be beneficial to use as well.
Yes, probably, depending on what you're trying to do.
To speed things up, let's say, it would be definitely...
Yeah, so what I would say is that, first of all, if you just put everything into NDArrays by itself, that's not necessarily going to make it faster. So if you have like code that was already written using regular JavaScript array of arrays, and then you just replace all instances of those with an NDArray, you should not expect your code to like all of a sudden magically get faster. Where it will get better is if you use the modules that are associated with NDArrays. So what you should do is if you have like a specific thing you want to do, like for example, like difference two images, you can use NDARRAY-OPS to subtract the two images. And then in order to call NDARRAY-OPS, you'll have to create an NDArray, and that's where the NDArray module would come in. So I would start, from the problem you want to solve and then work backwards through the modules on NPM that solve that problem. And many of those will lead back to NDArrays because they're built using NDArrays as a common language to talk about multidimensional arrays.
Do you see a point at which, people that are would normally use, Python, SciPy, or whatever, would start to be able to use some of this instead of,
Well, yeah, long term, that's the hope, right? Yeah, that would be great. The reason to do it, I think, in JavaScript, like I said initially, is better modules and the ability to put stuff in a browser, which right now you don't really have with JavaScript or with Python. And if you want to do things that are interactive, I think it makes a whole lot of sense to do it with JavaScript because there's just no good way to like run Python in a browser efficiently. So that's that. Okay, it's now like 7:06, so I can do like a demo or something. I can show a couple of different things here. Although it might be easier if I can get on. Or maybe Sean has his own demo that he wants to run too. I don't know if I've like chewed up all the time. I can show more stuff too. Which one do I go?
Was anyone able to get on the wireless?
Yeah. Yeah, okay, rather than fight with the wireless here, I think I'll just let you do some demos.
Did anyone else want to demo? I didn't know they're working on it.
Let me know if you change it. Yeah, try the wireless. Let me know if it doesn't work. That might be an old password. All right, so one of the things I wanted to show is actually a project where I'm using NDArrays, which I thought was pretty cool. I didn't know that you had written it. I just looked on NPM for multidimensional arrays, and I was trying to find something that would be sane and useful. I don't remember the specific options at the time, but NDArray seemed to be the best one that I tried, so I ended up using it. And I used it for this image diffing tool that I just call image diff. But I committed the sin you mentioned where I'm using NDArrays directly, and I'm sure the code is awful. But as you can see, I'm obviously just iterating over it. So I'm definitely going to look into CWise and the NDARRAY-OPS, try and repackage some of those. Because the problem is this is really slow right now. But this is a pretty cool module. I actually don't have a screenshot, but I do have. I did show it in a screencast. YouTube's SEO is not amazing. Oh, because it's trying to say, oh, did you make something else? Is it unlisted? I don't even know. Sorry. I know where I can find a link to it. So I made the screencast of Testium, but it also shows off this module that Testium uses. So you can compare screenshots. And in a second, these are the two screenshots. So one you can see is larger than the other. So they're different heights and widths, but they have the same core content. And then this is where it actually uses these pink pixels to show you where things are different between them, and then transparent edges where they don't overlap, which I thought was kind of cool. The reason I wrote this at all is because I couldn't find a synchronous JavaScript image diffing tool, which sounds oddly specific, but that's exactly what I wanted. I couldn't find it, so I just tried playing with NDARRAY until I got it to work. But the problem is it's super slow. It takes like over 10 seconds to diff screenshots of any size, of any real size. But hopefully once I use some of those other modules, it'll be faster. But it's still pretty cool. It doesn't do the really fancy things that you can get on like GitHub image diffing, but within Testium, that testing tool that I wrote, you can synchronously diff images, which I think is pretty neat. As far as Testium itself, it's in its own organization now. There was already a Testium user, which is not me, it's some Java thing. But, so it's under group on Testium if you're looking for it. But one of the other things I extracted was this Selenium download module, which is nice because I actually had a couple different projects where I just want to download the latest version of Selenium and have it locally and make it run. And that's all that this does, which is pretty nice. It sounds way simpler than it actually is, but if you look at some of the code, I mean, it's still not super complicated. But let's grab. So the way this works, if anyone knows a better way to do this, definitely let me know. But Selenium stores its binaries on through Google Code, which uses the Google storage stuff, and it just gives you this XML that vaguely describes what it's looking at. So I actually have to hit this URL, parse the XML, figure out what the hell version I'm supposed to be downloading, then go and download it. So it's just messing with a lot of this. You see a bunch of it's in a try catch just in case they change the format or something slightly goes awry. I don't know. It's really nice that this messy logic is self-contained now. So if you were writing your own tool or you have some other purpose for wanting Selenium, you can use Selenium download, and it has just this really small API. And sure, just make sure that it exists in a certain directory. If it's already there, it does nothing. And update forces an update in case, like, you know there was an updated Selenium version, and you want to make sure that you have the latest one, so it will force an actual download of the latest one. This also does, it's not MD5, it's CRC checksum checks, because the Google Storage API actually does return what those checksums are. So it'll make sure that you have the unmodified binary that you're looking for. But it's for Selenium and the Chrome driver that they also host, which I thought was pretty cool. That's really all I wanted to show.